All right, we'll begin. But yes, thank you to those of you who came, and if you're watching online, thank you for tuning in to keep up on course content. That's important. So, good job you for clicking the link. Anyway, yeah. So I sent out the email, but I'm not going to take attendance anymore. So I don't know what's going to happen. All right. I hope nobody at UCLA gets sick. Okay, that's what we're hoping, right? But I guess to minimize even personal interaction, because we want to keep that to a minimum, right? I'll also have the option for virtual office hours. So I'll just continue to have regular office hours, but then I'll log in to Zoom, and you can log into Zoom and then ask questions that way. It's just a little bit of extra work, so I just wanted to make sure some people would actually use it if I go through the trouble of setting up these Zoom meetings. It's not like super hard, but it's like, it's probably like 12 clicks, okay? So if nobody was going to use it, I wasn't going to use it. If no one is going to use it, I wasn't going to go through the trouble, but it seems like people will use it. Okay. All right. Well, today we'll talk about the bootstrap, which is another resampling method. Okay. So on Monday we covered randomization tests. Randomization tests apply in situations where your data was gathered via an experiment where random assignment was used. And if that's the case, then this assumption of exchangeability is valid, and you can simulate the conditions under the null hypothesis by re-randomizing the data. Okay, so we're doing something similar with Bootstrap. Okay, and we're basically trying to generate sampling distributions. And so I've talked about sampling distributions, but this is kind of a very key central idea. So here I go talking about it again. Okay. So, the sampling distribution of a statistic, whatever it is the distribution of all possible values of a sample statistic from all possible random samples drawn from the population, all right? And we can use the sampling distribution to see how much a particular statistic can vary. And then if you have the data, you can compare the statistic from your observed sample versus the sampling distribution under the null hypothesis, and you can see, what's the probability of producing your observed statistic from randomness alone, right? Okay, and kind of a key idea that appears, at least in the intro stats class, is the central limit theorem, and that basically says if you're looking at the sampling distribution of the sample mean, then it's going to be normal, okay, as long as these conditions have been met, as long as the sample size is big enough, right? And so x bar comes from the normal distribution, centered at mu, standard deviation sigma over the square root of n, right? Okay. You can have a sampling distribution for any statistic that can be calculated from a sample, right? So you can have a sampling distribution for the slope of a regression line, right? Because that slope of a regression line is calculated from a sample of bivariate data. You fit your model, you fit a regression line, and you could just imagine if you took a different sample, you would get a different slope, and then you would have, basically, you can have a sampling distribution for the slope, right? So any statistic you can think of, any value that can be calculated from a sample, ultimately has a sampling distribution associated with it, okay? But the sampling distribution of these other statistics, say like the standard deviation or something, is not necessarily going to follow the central limit theorem, right? And so they're not going to necessarily be normal. So what do we do in those situations, right? So, one way is we rely on our mathematical knowledge of probability distributions, right? So you take 100B, or you're taking 100B, and you learned all of the different relationships between distributions, the normal distribution, the chi-squared distribution, the whatever else, t distribution, and f and gamma and beta, and all of those are covered, right? Okay. But if it's like 6 weeks after 100B is over, maybe you've forgotten a lot of this stuff and you don't remember all the relationships between the distributions. Well, one thing that you can always do is you can simulate the sampling distribution. And I think this, I don't know, at least for me, it's easy for me to write the code to simulate a sampling distribution, right? Versus remembering all of the mathematical relationships. You should learn those, but especially if you're thinking of grad school or something. But if you can't remember them, this is always going to work, okay? And so the key here is that these simulations, and this is true for all of statistics, is that you have to make assumptions about the population, okay? You make assumptions about the population, all right? So you might make assumptions about the population's shape, or its mean, or standard deviation, or what values appear in the population. We're always making assumptions, right? Because we only get to see a sample of data, and we have to kind of fill in the rest of the picture by making assumptions about the population. And as a side note, sometimes, when you meet people, they say, oh, what do you do? And I'll tell them, oh, I teach statistics. And then sometimes people will go, ugh, and, that always hurts my feelings. When they talk about how much they hated their statistics class in college or whatever. And I tell them it was the best class I ever took. And, well, anyway, but, so that always hurts my feelings. But another thing that also bothers me is sometimes people say, oh, yeah, with statistics, you can say whatever you want, okay? Also, false, not true. You cannot say whatever you want. But one reason why people might believe this is because it's true. Two different statisticians could come to different conclusions because they have made different assumptions about the population, okay? And you just have to ask, what were the assumptions you made? And there might be compelling reasons for making either kind of assumption, right? Because at the end of the day is the population is something that we don't fully understand or don't fully know everything about, so we have to fill in the gaps by making different assumptions. And all of these assumptions we make should be justified or justifiable, but yeah, if you make different assumptions, it could lead to different conclusions, all right? So anyway, once you've established your assumptions, then you can simulate the sampling distribution by repeatedly drawing samples and recording the sample statistic for each sample. All right, so so this process we might call the parametric bootstrap, right? So if we are going to make parametric assumptions about the population, this is going to create a process known as the parametric bootstrap, okay? So this is, I don't know, these first two bullet points are completely unnecessary, but I thought they were fun. Okay, so the bootstrap idea, this comes from the phrase, pull yourself up by your bootstraps. Origins of that phrase itself are disputed. One theory, all right, is that there was a German folktale about the hero who was walking along, got stuck in a swamp, and to get himself out of the swamp, he grabbed his bootstraps, pulled himself out, right? So, of course, ridiculous. But it's kind of the idea that you help yourself out without getting outside help, right? It's, don't ask for free this and that. Just work hard and, I don't know, right? Pull yourself up by your bootstraps type of thing, right? And so the idea here is, you have a sample of data, and without gathering more data, help yourself out, right? So what that means is we're going to have to make some assumptions about the population. And in this case, we're going to make parametric assumptions, meaning that we assume the population follows a specific parametric distribution, right? A lot of times we'll use statistics from our own observed sample to help us specify the distribution. Not always, but it's a lot of times that we do. And then once we make assumptions about the parametric shape of the distribution, we'll draw many random samples from this assumed population. And then for each sample we draw, we calculate some statistic. We record this for every single random thing. We do this thousands of times. This generates a sampling distribution, and then we can perform statistical inference. All right, so that's so it's a lot like the randomization thing, except we're not doing random assignment, we're drawing from a population that we're assuming, okay? All right, so here is some example, right? So you guys took the SAT, I'm assuming, maybe? Okay, so do you guys still call it SAT verbal, or do you call it by its official name, evidence-based reading and writing? Okay, what?
Verbal.
Verbal, right? It's like math and verbal is the thing?
The acronym is too long.
Huh? Yeah. It's EBRW, right? Says, right? But yeah. So okay. But anyway, so there's SAT, math, and verbal. They're supposed to be, each of these are supposed to be normally distributed with a mean of 500 and standard deviation of 100. Okay. If you look at the actual distribution of scores, it's a little bit off because the typical SAT test taker is not reflective of the general population. Okay. But as far as the general population, it's supposed to be normal with a mean of 500, standard deviation of 100, okay? Except the maximum is 800, the minimum is 200, and it goes up in increments of 10, okay? So let's say we take a random sample of 15 students, and then the question is, what is the sampling distribution of the sample variance S squared, right? So if we take this sample of 15 students, and we calculate the variance of this sample, right, I get the S squared value, right? If somebody else took a random sample of 15 students and calculated S squared, and someone else took another random sample of 15 students and calculated S squared, and you do this lots of times, what is the distribution of S squared? You guys remember from your 100B? This was covered in 100B, maybe? Sampling distribution of the sample variance?
Chi-squared, right?
Chi-squared, all right. Points for you, okay. All right. So anyway, but maybe you don't remember chi-squared, okay? So what can we do, right? So here we can just simulate this thing, right? And even, this is not like totally normal. It's normal, but then I have to do some stuff to it, okay? And it'll still work, okay? So here I generate a sample, right? I'm assuming my population is normal with a mean 500 and standard deviation 100, and I use our norm to generate 15 values from there, okay? And then I use round -1 to round to the tens place. And then I run an if-else so that anything bigger than 800 becomes 800, anything smaller than 200 becomes 200, okay? And so here's just a sample of 15 values. And if I take the variance of this sample, I get 10120.95. Okay? So around 100 squared, around 10,000. Okay? And then so here's, I'm going to build up, simulate the sampling distribution. I just say we're going to do 10 to the 4 of these things. Okay? For I in each of these things, we follow that process. Random sample of 15, round them off, make sure the max is 800, make sure the min is 200, calculate the variance of this sample, and then store it away in sample variances, okay? And I just do this 10,000 times, all right? And then so here are my summary statistics. My mean is around 10,000. My median's a little bit lower. Max is close to 30,000. My min is down at 1,500, which is really low, but first and third quartile are around 7,000, 12,000. Okay, and here's the graph. Okay, sample variances going anywhere from 0 to up to 30,000. Here's kind of our frequency here, right? Okay, and so yes, the answer to our pop quiz, chi-squared distribution, right? So if x are IID from the normal distribution, S squared is the sample variance, then if you take the S squared and you multiply it by this constant, n-1 over sigma squared, then that will come from the chi-squared distribution with n-1 degrees of freedom, right? And so if I do that, if I take my values, the sample variances, and I multiply it by n-1 over sigma squared, I call this my scaled values, and I plot that, we get the theoretic is in red, and the actual is this, and we see a pretty close match, okay? Even though I like kind of altered them by truncating the max to be 800 and the min to be 200, and rounded things off to the tens place, okay? Still looks pretty good, right? Okay, but again, if you don't remember all of these distributional relationships, right? Parametric bootstrap gets around this by simulating the sampling distribution directly, right? And I think if I said do this, right, like make a sampling distribution, I think you could figure this out, right? It's basically just draw a random sample, calculate the statistic that you're looking for, and store it away, okay? So it's not too hard, right? So here's a problem, right? Let's say you get a sample of 15 SAT scores where the sample variance is 20,000, right? Is it reasonable to believe that this is a random sample drawn from the population where the mean is 500 and standard deviation is 100, right? So your null hypothesis is that the standard deviation is 100 versus that it's more than 100 or something, okay? And you can get an empirical p-value by comparing our sample variance of 20,000, which is what we observed, to the simulated sampling distribution, which we've already generated, right? So I've generated all of these sample variances, and I can just say, what proportion of my sample variances is greater than 20,000, okay? So sample variances greater than or equal to 20,000 generates a true-false logical vector. I calculate the mean to see what proportion is true, about 1%, okay? 1.2%, 0.012, right? So the interpretation of my p-value here is according to our simulated sampling distribution, you know, a population with a mean, population with a standard deviation 100 could produce a random sample where the variance is 20,000 or more, okay? But that's only going to happen with a probability of 0.012, all right? So this empirical p-value is low enough for me to reject the null hypothesis and conclude that my sample of scores is not a random sample from a population with mean 500 and standard deviation 100, right? So, because this says it doesn't happen very often, right? Okay, we can try some other thing, right? So let's say we're continuing to work with SAT verbal scores, normal distribution, mean 500, standard deviation 100, you know, with all of those other things. All right, let's pretend we have a classroom with 25 students and that these students are a random sample, right? That's a bad assumption, but because classrooms are never random samples. They always put the smart kids together and the bad kids together and stuff like that, right? That's just for efficiency, right? So how you did in 6th grade determines, yeah, whatever, okay. You guys all did great in 6th grade, and so you were put on the honors track and you were all with the college-bound students in your class, right? I'm assuming. Probably a safe assumption, but okay. But anyway, what is the sampling distribution of the highest score in the sample, right? You got 25 students. What's the sampling distribution of the highest score, right? Or what's the probability that the highest score in a random sample of 25 is 750 or higher, right? So that would be considered a good score. What's the probability that the highest score is 750 or higher, right? Okay, so technically there is a theoretic distribution. It's called the Gumbel distribution that can be used to describe the extreme value in a sample, right? So you can talk about what max value and stuff, right? But I forgot how to use this thing, right? So it says, you know, and so I just wrote, I doubt that many people know this or are familiar enough with it to use it, okay? I'm sure we could read up on it and figure this out, right? But easier, in my opinion, is just use the parametric bootstrap, right? So this is just kind of like, oh, I've got the power of the computer. Let's just almost like brute force figure this out, okay? We're just gonna throw the computer's random abilities and we're gonna say, well, what's the probability of this, right? Okay, so again, key assumptions, we're assuming what the population looks like. We're assuming it's mean is 500, standard deviation 100, right? And then we use computer's randomness to generate samples, simulate the sampling distribution. Okay, so this is all I'm doing, right? Pretty much the same code. This time my sample size is R norm 25. And then what's the value I'm recording? I take the maximum of my sample and I store it as the highest score. Okay? And I just do this 10,000 times. Okay? All right. And so no surprise that the max of all of these things is 800. Okay? And you know, most of the time we're somewhere around 690 700, something around there, okay? Sometimes we get over 750. So this is kind of the graph, right? So probably the gumball is not going to work because now I've like truncated the thing, so we get kind of this artificial, not a smooth tail down here, but it's truncated at 800, okay? So here's just kind of our thing, but we got a question, right? So this is what the distribution looks like, okay? And what is the probability that the highest score is 750 or higher? Well, we just say, okay, well, I've got 10,000 of these things, and I say, of those 10,000, how many are greater than 750? So it looks like it happened around 16% of the time, okay? And and that's it, right? What if I change this? What if we had a sample of 50 random students instead of 25? Okay, what's the probability that my highest score is over 750? Okay, well, again, it's easy. All I have to do is just modify the command. Now I take sample sizes of 50 instead of 25. The code is exactly the same as before, and now my answer is around 30%, okay? So if you take samples of size 50, what's the probability that your highest value is 750 or higher? Now it's closer to 30%, okay? And so this parametric bootstrap, we can answer a lot of probability questions just by simulating the sampling distribution ourselves. All right, is that okay? All right, so let's talk about the non-parametric bootstrap, okay? This is if you just hear bootstrap and people didn't say parametric or non-parametric, they're most likely referring to non-parametric bootstrap, okay? So if they just say, let's just use bootstrap, okay? They're almost, in general, referring to non-parametric bootstrap, okay? So the difference here is that non-parametric bootstrap does not make any parametric assumptions on the distribution of the population, okay? So we're not going to say the population is normal. We're not going to say the population has this distribution or that distribution, okay? We just, we don't do any of that, okay? We still have to make assumptions though. This is there's no getting around making assumptions. So in non-parametric bootstrap, the assumption that we're making is that our sample, that because our sample has been drawn randomly from the population, it can be expected to be representative of the population, right? Is that a reasonable assumption, right? So if you say, here's a random sample, you say, okay, here's my random sample. Because it's random, I'm expecting this thing to be representative of the population. Okay? All right. So if I kind of explicitly lay out what exactly this assumption means, it might make you feel uncomfortable, right? Because there's quite a bit going on. But I think this original statement, okay, so just think back to the original statement. If you're comfortable with the original statement, then you've got to be comfortable with all of this other stuff I'm going to go with, okay? The original statement was, my sample is a random sample from the population. Is it reasonable to say my random sample that I have is representative of the population, okay? And if you're comfortable with that, then you've got to be comfortable with this other stuff I'm going to be doing, okay? But because I'm making explicit, a lot of people get uncomfortable with it. Okay, so the idea here is now, because this sample I have is representative of the population, what I can do is I can clone it, okay? I can copy and paste it a whole bunch of times, and now I have a big group, and I'm going to call this my population, all right? So it's kind of like, I don't know, in Photoshop, maybe you have like a patch of grass, okay? And then you use the clone tool, and then you copy and paste it over like people you don't want to see, and then you fill in a big field of grass, right? And you say, well, this little patch of grass has to be representative of like general grass, so I can just copy and paste this, right? And from a distance, you're like, oh yeah, that looks like grass, right? But then when you look closely, you're like, wait a second, this funny looking blade keeps showing up everywhere, right? So that's basically what we're doing, okay? We're gonna say, here's my random sample of data, it seems reasonable to think this is representative of the population. So what I'm going to do is I'm going to basically copy and paste it. I'm going to use the clone tool, okay? And now I've got this big thing. I'm going to call this the population, okay? We don't technically, as far as the computer goes, we don't technically have to do this copying and pasting and cloning it, right? If I take the sample and I sample with replacement from the sample I have, that is mathematically equivalent to taking my sample and copying and pasting it infinite number of times. Okay, so you could think of like you can take like a deck of cards and you can stack like 50 of them together, or you could just take a deck of cards and then every time you draw a card you put it back and you're sampling with replacement, and they would be pretty much equivalent. Okay, sampling with replacement is equivalent to copying and pasting your sample an infinite number of times. Okay, and then so we use that quote unquote population to generate our sampling distribution. Is that okay? Does that make sense? All right. All right, so here's, maybe I should highlight some of these things. Okay, so here's some key takeaways, right? So if the data you have came from random sampling, you can use non-parametric bootstrap, right? If the data you have came from random sampling and you're willing to make parametric assumptions about the population, then you can use parametric bootstrap, right? If the data you have came from an experiment with random assignment, then you can use a randomization test, right? So these are kind of the different resampling methods that we're doing, okay? And in any case, in all of these, we're creating a sampling distribution, where randomness is kind of the key factor here. Yeah?
Wait, so in a parametric bootstrap, we can sample without randomness?
No. Parametric bootstrap, we are using randomness, but we're using randomness of some specified distribution.
Oh.
So we just say the population is normal, or the population is gamma, or the population is this, some probability distribution that, R has, right? So R has like R beta and R norm and R gamma and R chi-square, and you can use any of those things and you just say, I'm thinking the population looks like this. Yeah. Okay, I just copied and pasted this from a textbook, okay? So in your next homework, which I'm writing up and I'll post soon, this is a problem that we do, okay? And it's free for UCLA students. You have to be connected to the UCLA network. So if you go home and you live off campus, make sure you VPN in, okay? Don't post illegal links to the textbook. The link I provide is legal. Your tuition money goes to the library and goes to these publishers to give us access to the textbooks, okay? So you've already paid for access to this textbook. Okay, so anyway, this is a study that the Center for Immigration Studies at the U.S. Census Bureau did, okay? And they were curious about the immigrant population from Latin America, okay, and specifically Mexico, okay? And it says, although the average immigrant is approximately 40 years old, large numbers are children who enroll in U.S. schools upon arrival. Their subsequent educational achievement affects not only their own economic prospects, but also those of their family, community, and the nation as a whole. So Stamps and Bohan studied the educational achievement of Latino immigrants by examining a random sample of the 2000 decennial census data, a subset of which is provided in the CSV file. One interesting research question that has emerged from the research is whether there is a link, association, not causal, right? Association between where the immigrants originated and their subsequent educational achievement. Specifically, the question is if there is a difference in the educational achievement of immigrants from Mexico and that of immigrants from other Latin American countries. All right, so year 2000 census data, so it's already 20 years old. And the data consists of 150 Latino immigrants living in Los Angeles, okay? And so these are the different things. The variables of importance, okay? One is going to be the measure of educational achievement level. Okay, this is a scale of educational achievement ranging from 1 to 100, in which higher values indicate higher levels of educational achievement. Unfortunately for us, they did not give us a definition of these things. So they didn't tell us, like, what does a 50 mean, right? Does 50 mean they graduated high school? Does 50 mean they got through 10th grade? We have no idea what these educational achievement numbers mean, right? So does, like, if somebody earns their bachelor's degree, what number do they get? If someone goes on and becomes a doctor, what number do they get? I don't know, okay? That information is not known. They just say they've turned it into a quantitative numeric variable, right? And then the other variable that is going to be applicable to us for this question is, did the individual immigrate from Mexico? And this is categorical 0 for no or 1 for yes, okay? And so this is just kind of I don't know, the first few things. So we got 59, 63.7. They might have added some noise in here. I'm not quite sure. Okay, and we're going to look at this column for Mexico. All right, so just for some exploratory analysis, let's say, what is the mean educational achievement score for non-Mexican, other Latin American immigrants? Okay, and that's 64.5, and we have 34 in our sample. Okay, and then for Mexican immigrants, the mean is 58.6. We have 116 in our sample. Okay, and the question is, all right, so the difference between 64.5 and 58.6 is 5.92, and the question is this difference statistically significant, right? All right, and so just furthering our exploratory analysis, these would be the medians, and the question is this median different? So these are immigrants from Mexico, these are the immigrants not from Mexico. Is there a difference basically between the mean? The mean is not plotted here, but presumably sort of close to the median, right? Here is a density plot, okay? And is there a difference here? It's hard to say, right? We're looking at this, it's hard to know. Okay, so the traditional analysis would say the mean achievement for immigrants from Mexico versus minus the mean achievement for immigrants from other Latin American countries. That difference is 0 versus not 0, okay? And this gives us a p-value of 0.04597, okay? 0.04597, all right? And so depending on your alpha level, you may say this difference is significant or it's not significant, depending on what you've done, right? But this is the p-value we get from running a t-test. Okay, this is how we would do non-parametric bootstrap, right? So for non-parametric bootstrap, what we're going to do is we're going to resample our original data with replacement, right? And basically that is assuming that our sample is representative of the population, and sampling with replacement is equivalent to making infinite number of copies of our sample and calling that thing our population. Okay. All right. And we'll build our sampling distribution for the quantity x bar immigrants from Mexico versus minus x bar for immigrants from other countries. Okay. If the null hypothesis were true, there should be no difference. Or that if we assume variances are equal, and if the null hypothesis were true, meaning that the means are equal, then we could effectively say that both values are just coming from the same population, right? So we're going to just say this is the population of all immigrants from all Latin American countries, and we don't need to distinguish immigrants from Mexico versus immigrants from other countries, because if the null hypothesis were true, they're coming from the same population. Okay, so that's what we're going to set up, right? And so So this is, again, we're going to say if the null hypothesis were true, the achievement scores for Mexican immigrants come from the same population as the achievement scores for other Latin American immigrants. With parametric bootstrap, we assume our sample of 150 observed achievement scores is representative of the entire population. And so we will draw 2 random samples by resampling the 150 scores with replacement, right? One's going to be size 116, the other size 34. And then each time we do this, we calculate the difference between the group means. We're going to repeat this many times, and we're going to estimate our p-value by saying how often our random samples produced results that were as extreme as the actual data that we observed. So this is how our non-parametric is going to work. So this is the code that we run, okay? I set up a vector for differences. We're going to say 10,000 of these things. I run a for loop, okay, for each of these things. And you can see this is quite similar to, the randomization test, except the big difference is here I'm doing a sample with replacement of the size. So we're saying this column, Latino $achieve, that's the 150 achievement scores that appear in our data, okay? And we are going to draw 116 values with replacement, okay, from here, okay? So we use replace equals true. We draw 116 values from there, and we're going to call that group A. And we're going to draw 34 values from the same population, and we're going to call that group B, right? And we just say, okay, well, what's the mean of group A? What's the mean of group B? What's the difference between those two things? And we're going to store that away as differences, okay? Because here we know that if there is a difference between group A and a difference between group B, it's a result of the randomness, okay? There's no other reason why group A or group B are going to be different, okay? Any result difference we see here, we know is purely from randomness while the null hypothesis is true. Okay, so we do that, and so the p-value that I observe in my data is going to be, we say, take the absolute value of the differences because my alternative is two-sided. I have a not equal sign, so we're looking at the thing, and we're going to say how often are the absolute values of the differences greater than or equal to our observed difference, which we calculated back here to be 5.9216. So how often are we getting differences of 5.92? And this says that happens around 4% of the time, 0.0465, okay? And, if we look back to our t-test, our p-value was 0.0459, okay? So we're getting something very, very close to the t-test is we get 0.0459, so basically 0.046, and here we're getting 0.0465, okay? So something very close, all right? And so this tells us that even when we draw random samples from the same population, sometimes we get mean differences of 5.9 from random chance alone. That happens just a little bit less than 5% of the time, right? And so whether we reject the null or not depends on our alpha, our significance level. All right. Is that all right? So this would be non-parametric bootstrap, and it's non-parametric because we made no assumptions about the population having a parametric shape. We just said, my sample, it's got to be representative of the population, okay? And under the null hypothesis, both values, both samples, both groups are coming from the same population. Okay, if we wanted to do parametric bootstrap, we could do parametric bootstrap for real data as well, okay? And we would set up our null hypotheses at the same time, same way. And again, under the null hypothesis, data for both groups come from the same population. This time, okay, yeah, 116.34. Okay, here's same stats, summary stats that we saw earlier. This time, the big assumption here is that we have to make parametric distributional assumptions about the population, right? So, if we go back to this plot, we say, well, could the population be normal? And we look at this and we I don't know, maybe, okay? So, I don't know, maybe it's not a good assumption, but you got to make some kind of assumption about the population. So let's just say that the population is normal, okay? So again, both, under the null hypothesis, both sets of data are coming from the same population. So we're just going to use the overall mean of all 150 people and the overall standard deviation of all 150 people as the mean and standard deviation of our population, right? So I'm going to take the entire column of 150 values, calculate the mean, the entire column of 150 values for achievement scores, take the standard deviation, and this time, when I do my sampling distribution, I do group A and I draw 116 values using R norm, and I draw 34 values using R norm. I store those and I take the difference in group means, okay? So it's just this part that makes it parametric. Here, I'm using R norm. I'm assuming that my population is normal, okay? And the other one, I didn't. For the non-parametric, I used sample using with replacement, okay? So it's parametric because now I'm assuming it's normal with this mean and standard deviation, and I'm using the mean and standard deviation from my set of data. Okay, and then I do the same calculations for my p-value, and this time I get 0.0466, which is pretty much the same as what I got before. I think I got 0.0465. When we do the t-test, we got 0.0459. So we're pretty much getting the same value in all three of these ways. So my conclusion here is pretty much the same, right? Agrees very, very closely. Okay. Again, when you do parametric bootstrap, you should check your assumptions. Is it reasonable to make these assumptions, right? And so this would be the histogram of achievement scores. All right, and we asked, does this look normal? I don't know. I would hesitate to say yes, okay? All right, and then when we do the plot here, does this look normal? Like, does that look like a straight line? I don't know. Again, I hesitate. All right. Oh, okay. And I had a sentence that basically said, well, maybe we shouldn't assume it's normal, okay? But, you know, central limit theorem to the rescue, right? We've got, you take a sample of 34, you take a sample of 116, that's over your kind of the sample size like minimum, right? And so central limit theorem kicks in and you say, all right, I can use the t-test and this agrees, right? So the empirical bootstrap the parametric bootstrap is great if you're willing to make these assumptions about the population. And then the non-parametric bootstrap is also great if you truly believe that your sample is a random sample and representative of the population, okay? But again, you have to think like, would I use the clone stamp tool in Photoshop to duplicate this patch of grass? You know, if there's like a red dot in the middle of your grass, this is not a good patch to clone, okay? All right, and so if you look at your sample and there looks something like a huge outlier somewhere in there, okay, probably doing non-parametric bootstrap is not a good idea because you would be cloning that outlier all over the place in your population, right? So the key assumption you're making in non-parametric bootstrap is that the sample you have is representative of the population, which may or may not be a good assumption. And that's the problem, is you went out and you gathered data and you have no idea, right? Like maybe if you understand the field very well, you can say, all right, these numbers seem reasonable, right? But sometimes you're doing an experiment and you're not quite sure what to expect. You get some data and you go, ooh, is this what the population looks like? Because it seems surprising to me. And you kind of have to go with it, and that's where we go. So all to say, you should have some base knowledge of this field where you're working with the data, right? So if you're going to work, you know, I don't have you guys do a project or in this class or anything, but like if you were going to do a project and you say like, let's go on Kaggle to find a data set, right? And you go on Kaggle and you're like, oh, here's some uh, you know, cancer data that some doctor collected, right? And you go, okay, this sounds interesting. It certainly does sound interesting. But if no one in your group knows anything about cancer data, like, you're going to be working in the blind, right? And then you won't know, like, is this thing weird? Is this an outlier? Is this something I should include or not include? Can I use Bootstrap? Like, there's a lot of questions that require some domain knowledge there. So, okay. Anyway, that's the Bootstrap, and we'll end here for today. And maybe I'll see you guys on Friday. And I'll set up a virtual office hours meeting as well. Or, of course, you can come to real life office hours too. All right. See you guys.